Engineer Phoenix and the APRA team for this honor. I feel honored to be invited for this session to facilitate things to do with auditing of steam systems and boiler systems. As Engineer Phoenix said, I've worked with KTDA majorly around the manufacturing of tea. Worked both in the regional offices as a regional engineer, and I've also worked at the head office as the development engineer in charge of new initiatives, new inputs revolving around energy. And yeah, I'm also a professional engineer and a licensed energy auditor, and also I'm a certified energy manager. So I think with those few remarks, I want to get straight into the presentation so that maybe we can have room for questions or any suggestions or any input from you guys. Basically, I'll structure the training as I'll share. I'll structure into an overview of STEAM. Then we go to auditing various segments of STEAM. That is the boiler system, the steam distribution system. And then we go to case studies. We look at the best practice and we go to conclusion. Yeah, so I think it's good if I'll start sharing my screen. Just hold on, I'm trying to. You can see the presentation in full.
Not yet, engineer.
Just hold on.
Okay. Maybe you can send someone where you are. Where are you? Are you Nairobi or Kericho?
I'm in Nairobi, yeah. Okay, hold on. It should be okay now. Trying to upload it. Wow. Perfect. Share. Can you see the presentation? Huh?
Yes, we can see it. Maybe you can put in the presentation mode. That is the.
Right. Thank you. Thank you.
Yeah.
So I'll maximize the screen and from the beginning. You're okay now? So I'll get started.
Engineer, at the bottom of your screen, there is this tab here which allows the slide to show in presentation mode. That is the, I don't know how I can direct you. The third tab after the comments. After comments, you see comments down
After
there.
comments.
Comments. After, yes. The third one, the fourth one. Sorry.
I'm using the web app. Share results. I thought I had already shared.
Yeah, it's already. shared. I think
Yeah.
you can proceed. Yeah.
It's okay. So, so basically, I'm on the second slide. So basically, I've outlined the presentation in terms of the steam system overview, efficiency in the steam boiler. Then thereafter, we look at energy saving opportunities in the
engineer. We
steam boiler.
cannot. You are still in the first slide. Eh?
That's the one showing my name.
Yeah. Go to presentation mode. Eh?
On the PowerPoint.
Yes, on the PowerPoint, after the comments, I think the third one. Eh? After down there, extreme right. Eh?
Uh-huh.
You can see where it's
On
written comments.
Yes. Oh, yeah.
The third one. Go to the number 3.
Oh, number 3.
Actually,
Oh,
number
yeah,
4.
yeah.
Number 4. You
Okay.
can.
Number 4. Number 4.
Yes.
And then click
4.
that. Eh?
Okay. Is that in order?
You've clicked.
Yeah, I've clicked it. Can you see the second slide?
Still in PowerPoint. I mean, it's not in presentation.
Engineer, let me assist. I believe you can share your whole screen, and then we'll be able to see you moving your slides.
All right. Okay. So
Yeah.
I've already shared the screen, right?
Yes. Just share the whole screen.
So I share the whole screen.
So you can stop sharing, and then you share the whole screen.
Where do I share the whole screen? Wow.
Just at share there. If you go to share, then believe there's some options. You can share window or the whole screen.
So share window, Chrome, entire screen. Okay.
Yes.
Yes, engineer. I would have Chirchir would have already reached town if you had told me where you are. He helps all people like me and you on these network things. Eh?
We are not growing younger. Can you see the presentation now?
Yes. Yeah, then you try to share now the presentation mode.
Yes, we can see it now. You can go to the part where you had been directed earlier. After the comment,
I've now
that
gone
was
to the
now
presentation. I've now gone to the presentation mode.
Yes.
Yes, now
Can you
try
see
to
the
scroll.
second slide?
You can go to.
Not yet. Yes,
Yes,
it's okay.
It's okay now.
Yeah, you can see the second slide. The third slide, can you see?
That's something new today. Eh?
Yeah, we are learning.
Yeah,
yes.
Okay, thank you so much. Thank you
fine.
so much. All right.
You can now go up and down.
I'm at the top. Yeah, you can see the first slide, the second slide. Yeah. Thank you, team, for assistance. I rarely use this. I normally use Zoom. That's why I'm not quite familiar with it. So I've structured this presentation into 5 sections. That is steam systems overview, then efficiency in steam boilers. Then we go to energy saving opportunities in steam boilers. We'll mention what we'll discuss in each of the segments. Then energy audit in steam distribution systems, then end-use equipment and steam consumption. I've split this into 2 main parts. That is boiler section, where we look at the boiler overview, then we look at the efficiency, how to determine the efficiency, calculate the efficiency in a boiler, then what are the energy savings opportunities in a boiler. Then we look at the how to audit the steam distribution system also and identify opportunities, identify losses in steam distribution systems. Then lastly, we also look at end-use plant and equipment and how we could save energy from that. So off we start. Steam is one of the most widely used commodities for conveying heat energy, and it's popular throughout industry for a broad range of tasks, ranging from mechanical power production to space heating and process applications. Why is steam utilized? One is that steam is efficient and economic to generate compared to other forms of energy. Steam can easily and cost effectively be distributed to the point of use because it behaves in a gaseous manner. Then steam is easy to control in the sense that the characteristics of steams is not like any other form of energy, like nuclear energy, where they have to be handled carefully. But you see, it can exist in a very inert state. Also, steam energy can easily be transferred to the process by use of radiators. Then steam is flexible in that it can nearly fit into any applications from processing food, pharmaceutical industries, health industries, and also it's used in hospitals for sterilization and for cooking. So let's look at heat energy available in steam. I believe all of us must have had this, must have interacted with this diagram. If you ever did thermodynamics, I believe all of us did that, whether you are an electrical engineer or an agricultural engineer or a mechanical engineer. I'll excuse the civil engineers here. Or if you ever did physics, industrial physics, you must have interacted with this diagram. And basically on the vertices, on the vertical, whatever, we have the temperature. Then on the horizontal, we have energy. And this is the behavior of steam as it transforms from solid state, that is ice, to liquid state, that is water, then to steam or gas or water vapor. There's something that is called latent heat and sensible heat. And the latent heat is what we'll focus on here because that's what is in the steam table. Whenever there's a phase change, there is either absorption of latent heat or there's release of latent heat. When steam is transforming, when the solid ice is transforming from water, from solid to water, when it's melting, you have to input energy into steam. At that time, the temperature remains constant. It doesn't rise, you're feeding it into energy. Then at the same time also, when it's changing from liquid to gaseous state, the temperature does not rise. It's observing energy, but there's no temperature change, but the phase change is happening from gaseous to water. At the same time, on the reverse, that's what is happening, and that's now what we are talking about when you are utilizing steam. If you look at this diagram, from here, I believe you are seeing it, from transitioning between liquid phase to gaseous state, it's two-way. When you are transitioning from liquid state to gaseous state, that's evaporation. That's what happens inside the boiler. You are burning, you are supplying energy. At the same time, when you are transitioning from gaseous state, that's now put this way. This is at the radiator, at the end use of equipment. That is from the steam distribution system to the end use equipment. This one is transitioning from gas to liquid. That's why you see condensation, and that's why you see the formation of condensate. Again, that heat is given out. It's given out to the process. Now that heat is going to be used in the process, either for firing, for drying, for cooking, for sterilization. Now, what are the common applications of steam? Steam is used in a wide range of industries, and here are some of the typical applications of steam. One is that steam is utilized in heating and sterilization. Steam can be used for heating in food and pharmaceutical industries, refineries, and when I talk of refineries, you find that refineries and chemical plants, there's something called fractional distillation. That's when you use steam. Then it can be used for propulsion, and a good example is in power generation, specifically our geothermal power plants. You find that the steam is the one that runs the turbines. GDC also applies the same. Then steam can be used as a motive force to move liquid and gas stream in piping, that is in pipeline operations. But I don't think this is applicable in Kenya. I guess it's in other countries. Steam can also be used for atomization, a process where steam is used to mechanically separate fluid. In some burners, for example, steam is injected into the fuel in order to maximize combustion. When you are injecting steam into the furnace, it's already like fire. So it vaporizes, and because of its gaseous nature, it's like blowing air, but air with energy. Then steam can be used in cleaning. Basically, if you visit a meat processing factory, you'll find that they use steam to sterilize surfaces. Meat processing, places like Kenya Meat Commission, dairy industries, Kenchik, where they slaughter the chicken, all those areas they use steam to sterilize surfaces. Then steam can be used for moisturization. That is, steam sometimes used to add moisture to a process while at the same time supplying heat to maintain appropriate process parameters. Then also steam is used in humidification, that is in HVAC applications. If you visit a place like the US Embassy, you'll see this application in the chilled water system. When the environment is cold, they supply steam to produce heat. And when the environment is hot, of course, they don't use that. So let's look at a typical boiler setup, a steam boiler setup. This is an oil-fired boiler, but there's not much difference between an oil-fired boiler and biomass-fired boiler. I think this will be my focus because we rarely have electric boilers. And when I talk of electric boilers, are the ones that use elements to fire, heating elements to fire steam, to generate steam. So basically, I think any typical boiler is set up like this. I'll start with the furnace, and then this is the furnace where the firing happens. And as you can see, this is the burner. That's number 3. This is the burner. The burner has oil mixed with air. Then inside the furnace here, what happens is combustion. And in this case, we endeavor to achieve stoichiometric combustion. Then if you look at the end plates, these are the end plates. This is the front end plate and this is the rear end plate. If you look at these holes here, which I'll explain later, these are the fire tube, where the flame travels. Then the flame travels, it goes, hits the end wall here, then travels back here, then travels back to the chimney and out. These tubes here are enveloped by a pool of water, which will now, which the fire tubes will transmit heat into and thus generate steam. We have also pumps that supply the feed water to the steam, to the boiler. Normally, in any standard boiler establishment, during your energy audits, there are always 2 pumps, but both of them are not operational at the same time. These are pumps that operate in a redundancy mode, and they alternate so that they don't it doesn't operate continuously throughout for the case of like getting equipment burnout or straining the equipment. So you'll find that one of the pumps operate for like 4 hours, then it alternates. This other one for 4 hours or 2 hours, depending on the setup. So whenever you're auditing a steam boiler, if you find one pump is missing, then there's a risk, because at 1.1, this pump is overworked and brings out efficiency issues on that issue of pump. Then you're not supplying sufficient water into the boiler. Yeah. Also, there is a risk factor. In case this pump fails and the other one is not operational, there is likelihood, and there's likelihood that you may not be in a position to supply steam water to a boiler which is operational, which is quite risky, and the boiler might fail. And our boilers fail. Actually, as we are talking, around 3 weeks ago, the 2 pumps failed in one of factories in KTDA. And the boilers failed. And it failed in the sense that there was no water inside the furnace. The steam has been fired, everything out. The cavity between the fire tubes and the shell remained empty. Then it got thermal shock. The boilers collapsed. And these boilers are designed to collapse inside. They are not designed to explode outside. This furnace here will just crash. You'll find this here meeting down here. So when, the thing is, these boilers always have to have two operational pumps at any one time. Then number 1 here, we have, these are the safety instruments. That is the temperature gauge and the pressure gauge. And the pressure gauge will have to give you readout of how much pressure your boiler is operating at any one time. Normally, like say for the T sector, most boilers operate at 10 bar, are designed to operate at 10 bar. Then you have the temperature gauge here. Yeah. So the temperature is telling you what the temperature the fluid is, but with pressure and your steam table, you should be in a position to know what temperature your boiler is. Then we have level controls here. That is number 9. If I can move the cursor here, we have the level controls here. I need to mention something about these level controls. You see, the water level in the boiler should always remain at maybe slightly above half, between say half and 3/4. Of course, not below half. Maybe slightly below 3/4 and above half. The water level indicator basically uses the capillary action. Like whatever level is inside the boiler will show you whatever level is outside the sight glass. They are normally called sight glass. And they are normally in 2 also, just in case one fails. And the reason why I say it, the water level always has to be maintained at that level, that is between 3/4 and half, is because you need space to accumulate steam. In my experience in the T sector, when I was a regional engineer in KTDA, is that at one point, because you see the boiler operators fear the boiler running without steam or without enough water. So what happens is they adjust the water level to a point quite high, say above 3/4, and they now fire the boiler. But you see, there's no enough space to accumulate steam. So you'll find that you keep stoking the boiler, feeding firewood, you're not generating enough pressure to fire your process. So you end up spending a lot or utilizing a lot of firewood or a lot of fuel for that case, while generating very little pressure. So, but if you adjust the level lower, slightly lower, and normally those guys are trained, any boiler operator operating a boiler in any establishment ought to have had this training. For KTDA, they normally take their training guys to this NITA trainings, or specifically to be trained on boiler operations. These are basic operational issues. So whenever you're auditing, you realize the water level is high, then obviously that's a red flag. You note those are operational recommendations that can be achieved without incurring any cost. Then, of course, we have here they've installed an economizer, and they mentioned something about that. Allow me not to mention anything right now about it. It's ahead. Then also we have the control panel here, where you can easily read out the parameters of the boiler, and you can overrun the automatic operation of the boiler either by switching on a pump, switching on the ID fan, or shutting down the ID fan. Basically, for wood-fired boilers, in this place of the burner, normally is a door, just like any other door that is opened. Then the firewood is stocked into the furnace, then it's closed. I'll mention something later also about it, but it's good that I mention here. That door need not to be opened frequently, because the moment you open it frequently, you draw in cold air, then you reduce the ambient, or what the air. So you reduce the temperature of supply air, of the combustion air that's inside the furnace, thereby you reduce the efficiency. All those you'll see as we go by. This is a typical, the next slide, this is a typical boiler and steam distribution system. At the bottom left here, this is the boiler. And we'll start with the journey here. So everything starts here. Now the boiler that we are looking previously. So we have the steam boiler here. Then we have what is called the main supply line to the header. Then we have the steam header here. Any setting must have this header here. You cannot pick steam here and supply it directly to the process. So you have the steam header here, which is supplied by the boiler. And here we have a stop valve, or a steam stop valve. That is, if you want to work on the header, you'll have to isolate here. Or if you want to work on any process here, you have to isolate the steam system here, the boiler here, then you work on it. Then after the steam header, then you have now supply lines, supplying all the other lines. Each of these will have a valve whenever you visit a factory. So from there, this is now the steam supply line. Yeah. Then it supplies to the heating unit. This is in practically, this is a radiator. Say you are dealing with a dryer. This is a radiator inside the dryer. Or this is a calorifier, or this is an autoclave. We are talking about a hospital. Oh, yeah. So after the heating unit, of course, you don't expect that all the steam that comes here converts into condensate. Some steam will escape, of course, because of efficiencies and airflow and flow rates of steam. Actually, you are generating steams at 4,000 or 5,000 kilograms per hour, and it's pushing through here. So some steam will try to escape the radiator. So we have something here called steam trap. And for this case, we are talking about a closed loop system. And I would wish to say that let's not focus on open loop, because I don't think there are any efficiencies we are talking about in open loop system. The moment you are opening, you are spilling the condensate out without recirculating it, there's no efficiency you're talking about there. So my focus today will be on closed loop system, but I'll mention something to do with open loop. So the steam trap will ensure that no steam escapes into the condensate line. So from the steam trap, it goes to a condensate receiver, and the condensate receiver goes back to the condensate receiver. After the condensate receiver, then we have a pump. Inside here, I'll still share at the end the steam distribution system itself now, the condensate loop. you'll see the setup for this condensate system recovery. Then this is normally a tank which supplies water to the pump. This is the feed water pump. You remember the two pumps I showed? This is the position it is on the steam system. Then it pumps back into the boiler. I think there's something I need to mention here, because I know I've not mentioned it ahead of the presentation, is that as an energy auditor, you need to be careful when auditing the condensate tank, or when you need to check out the position of the condensate tank in relation to the pump and the boiler. Normally the pump is just next to the boiler. Sorry. Normally the pump is just next to the boiler. And I guess the guy of the pump would have mentioned it clearly and more much in detail. But from my experience in steam, is that the height between the steam, the condensate tank and the pump is quite critical on the efficiency of the boiler. Because it will ensure that you supply enough water into the boiler. The moment this height is small, then this pump has what is called net suction head. Any pump, if you look at that book from Davis and Shackley, there's the supply head and there's the net suction head. One is that the moment this height is low, which means, and this pump is sucking, you'll tend to create a vacuum here. When you create a vacuum here, there's something called cavitation on pumps. I think my colleague would mention it in detail. That cavitation means that at one point you'll be supplying air here and at the same time reducing the life of the pump. But those are maintenance issues, but it will mean that you're not supplying enough water to the boiler, then you reduce on overall output of the boiler also. Let's go to boiler types and designs. There's a diagram here, so let me just describe here, then we look at the diagrams. So there are two broad categories of boilers based on how the flame travels inside the boiler. We have one, we have the fire tube boilers, and then two, we have the water tube boilers. Basically, the two describes what travels inside the tubes. For fire tube boilers, the flame, that's the example I gave, and that's what is the most common boiler here in Kenya and even in the world. In fire tube boilers, the flame travels through the tubes. Then the water envelopes the fire tubes. Heat transfer happens by the water coming in contact with the water tube, with the fire tubes. And the design normally is that the fire tubes are corrugated, ribbed, sort of. Then inside the fire tubes there are spirals, just to delay the flow of the flame for maximum heat transfer into the boiler. If you open that boiler, normally you see things that look like streams, not streams, springs. Those springs serve to delay the flow and ensure maximum contact with the boiler. During your energy audit, if you find that most boiler operators, for ease of maintenance, they tend to remove those springs and put it aside so that soot and ash don't get retained inside the fire tubes. But when you remove that, the flame will just be traveling in one direction outside into the chimney without much heat transfer, and that affects boiler efficiency. But if you have those tubes inside, then not the tubes, the springs inside, you kind of create a spiral flow of the flame, thereby guaranteeing maximum heat transfer. In fire tube boilers, there are two further types of fire tube boilers. We have wet back boilers and we have dry back boilers. in wetback boilers, I'll show you in the next diagram, is that as the name suggests, the reverse chamber is surrounded by water. And as you can see in this figure, the combustion reversal is surrounded by water, and therefore the heat in the flue gas is optimally utilized. Radiation losses are reduced as none of the combustion chamber are open to atmosphere, and instead they are surrounded. Then we have the dry back. The dry back is not completely surrounded by water. The posterior part is exposed to the atmosphere. This leads to the radiant heat. This leads to radiant heat is as the radiant heat is lost to the atmosphere instead of going to the water. As in wetback boilers, earlier generation of boilers use wetback. Water tube boilers, I'd explained, they're not so common, but these are the two common boilers here, wetback and dryback. So this diagram clearly shows now how the flame travels in wetback and dryback boilers. So this first diagram here shows the bottom here is the first pass, that's the furnace. Then there's the reverse pass. There's a separation here where, because the chimney is up here, so there's a separation here. And that's why it's by a water surface. That's why it's called wetback. That's why it's called wetback. So there's a second pass here, then there's a third pass here. Normally, wetback boilers are 3-pass boilers, and they're the most efficient because as you can see, the flame travels 3 times in the water tube inside the boiler before getting out of the chimney. And as you can see also, if you visit any factory, how do you identify a wetback boiler and a dryback boiler? A dryback boiler has only 2 passes, 1, 2, and the flame is out. The way you can identify a wetback boiler is it has 3 passes and the chimney is at the rear. From the furnace doors, the chimney is at the rear, at the end of the boiler. While for a dryback boiler, the chimney is in front. You'll find that the chimney is in front of the rest of the settings are the same. So, and talking of efficiency, you can see that there's more time here for heat transfer. So the wetback boiler is the most efficient compared to dryback. But maintenance, of course, dryback is the easiest. Yeah. So let's look at heat and mass balance of boiler at normal operation. So at normal operation, you're supplying fuel, yeah. You're supplying water, what goes into the boiler. Then what is the output of the boiler? Now, fuel supplies energy, water takes in the energy from the fuel. Then we have the flue gases taking out energy. Then we have heat losses due to radiation. That is if the boiler is not insulated, which is normally the case in most of our settings. Then we have the vapor, which is now the steam. That's an output also, taking away energy also. Then you are returning condensate with some level of energy. If you look at this, this is kind of the boiler house or the steam system envelope. So I'll repeat. What comes in is fuel supply, feed water, and the condensate. And electricity, of course, for running the ID and that is FD fan. For those who do not know, ID fan is the induction fan that sucks air into the furnace. Then FD fan is the forced draft. It throws in air into the furnace. Those are terms you need to be familiarize yourself as an energy auditor. Then we have the blowdown also, because on a regular boiler operation, you must do the boiler blowdown. I'll mention something to do with it later. This is to remove the total dissolved solids that are inside the boiler to guarantee that there's no sludge that accumulates inside the water side of the boiler. So let's now talk about efficiency in steam boilers. So normally efficiency in steam boilers, some boiler manufacturers often cite when they are selling you a boiler, or if you look at the nameplate of the boiler, you will see that this boiler has a thermal efficiency of this. Of course, they'll indicate the pressure. The best thing as an energy auditor, the first thing you do when you visit to audit a boiler or a steam system is take a picture of the nameplate of the boiler. It has a lot of details. It has the year of manufacture, the operating pressure, the efficiency, and this time combustion efficiency. I mentioned things to do with pressure downstream. The combustion efficiency, then the fuels to steam efficiency. Some are quite generous. I know JTA boilers, John Thompson boilers normally indicate all this. Thermax, some are serious. They put it, some they don't put it. Yeah. So let's talk about thermal efficiency. Thermal efficiency reflects how well the boiler vessel transfers heat, and this figure excludes radiation and convection losses. Thermal efficiency, that is how it is transferred from the fire tube into the water inside the shell tube, the shell of the boiler. Yeah. So you can now relate by just looking at this statement. You can relate the thermal efficiency of, say, a 2-pass boiler and a 3-pass boiler. That is the wetback and dryback, dryback and wetback boilers. You can clearly see. Combustion efficiency indicates the ability of a burner to use fuel completely without generating carbon monoxide. I think this one is pretty much direct. We are talking here of can we achieve stoichiometric combustion, where you burn fuel here, then at the chimney you only have carbon dioxide and you have water. Because when you burn any hydrocarbon, that's what should come out. It's not normally the case. We'll also mention how to, along the presentation, we'll mention how to measure. That's combustion efficiency. Fuel to steam efficiency. This is accepted through input, output. How much fuel have you used and how much fuel steam have you generated? The rate at which you use fuel per hour and how much steam are you generating per hour. Those are, when you compare the two, you can easily know how efficient your boiler is. So during your efficiency, you need to be in a position to present these findings in your energy findings and make recommendations on how to improve the thermal efficiency. And as I was telling you, thermal efficiency, you will find the boiler operators because they want to easily operate the boiler without much flow. They remove the spirals. Yeah. Combustion efficiency, yeah, you'll find that they frequently open the boiler furnace, you let cold air in, then you have excess air on the outside, you have carbon monoxide because of incomplete combustion, or they overstock the furnace until there isn't sufficient airflow. So the boiler furnace starts looking like a kiln, or to put it in perspective, the car kuchoma makaa. Yeah, if you open that boiler, you'll see charcoal burning inside. That is not an efficient boiler. There is a way of stocking also the furnace. You are supposed to leave room, just like the water. You are supposed to leave room for sufficient airflow, so that the stoichiometric combustion happens. So what are the factors affecting boiler efficiency? There are 5 main key parameters used to determine boiler efficiency. I'll touch on them briefly, each of them. We have the boiler start temperature, and what I'm talking about here is the temperature of the flue gases as they leave the boiler. This temperature represents a major portion of the energy not converted to usable output. And in essence, you find that the higher the temperature of the less energy transferred output, and the less energy transferred, and the lower the boiler efficiency. It's pretty simple like that. If you go to a boiler house and you find that the stack temperatures, these are things you need to read. Normally, every chimney has a temperature gauge installed on it at the stack, just at the exit of the furnace. You need to read that the temperature reading and not. And even they're supposed to be recorded on a daily basis also. There's a book that records all this. Yeah. So if you find that, say, that temperature is reading something like 200 degrees Celsius, that is an inefficient combustion. Yeah. In other words, that's an inefficient boiler. What is causing it? Are you overfiring? Are you supplying too much air in it? Or is there less flow inside the boiler? Or the pressure drop across the boiler is too low, so that there is no, the resident time for heat transfer doesn't happen, so that it escapes inside the boiler. Those are things you need to find out. So you need to check the ID fan. Is it running in appropriate revolutions? Guarantee you that it's sucking, it's creating sufficient draft. Yeah. Does it have enough pull levels? Believe you me, if you go to most of these boiler houses, you'll find some fans even running at instead of 5 pulley bells, V bells, you'll find them running with 1 or 2 V bells. And the boiler is still running. Fuel specification, and what I'm talking about here is moisture content. Specific for HFO, I can't mention much about it, but for for biomass, what is critical here is the moisture content. Also, I've done a table below here at the end of this presentation, which shows the moisture content and how much calorific value each biomass has at specific. So that these are records that you need to have also check and see how they've been consuming, how they've been utilizing their steam. So then for this one also, you need to go back as an energy auditor and check, are they storing their firewood or their biomass in a sheltered place free from weather vulgarities or especially rainfall? Yeah. So you see, the higher the moisture content, the more vapor is formed during combustion. The result is energy lost as the vapor absorbs energy in the boiler and lowers the efficiency of the boiler. It's as basic as that. Then you need to mention about heat content of the fuel. I guess it's related to the above. There's a table there that shows various calorific value of each and every fuel. We've talked about wood, we've talked about coal, we've talked about peat, we've talked about gas, yeah, all those. Then we have excess air levels. Excess air is supplied to the boiler beyond what is required for complete combustion. Excess air, however, uses energy. You see, when you overpump, when the ID fan is oversized, yeah, so it tends to suck out it instead of now ensuring resident time for combustion. Then we have ambient temperature and relative humidity. That is, the lower the ambient temperature, of course, the boiler has to work hard to bring to level the ambient temperature to the furnace. You remember the heat generated is Q times delta T. Yeah. So that delta T will mean now the lower the temperature, you'll pump in more energy just to bring this level to this, to bring the lower temperature of the ambient air to the one that now can come into, the one that goes into the furnace for firing. Yeah. Then, so what are the combustion efficiency indicators? As a rule, the most efficient and cost-effective use of fuel takes place when the CO2 or carbon dioxide concentration in the exhaust gases is maximized. Theoretically, this occurs when there is just enough oxygen in the supply air to react with all the carbon in the fuel. The absence of any oxygen in the flue gases directly indicates deficient combustion air, while the presence indicates excess air. Ideally, the oxygen levels shall be maintained close to 2 to 4%. Yeah. Then carbon dioxide is a sensitive indicator of incomplete combustion. Its levels should range from 0 to 400 parts per million by volume. The presence of a large amount of carbon monoxide in the flue gas is a certain indicator of deficient air. During your energy audit, you cannot go to audit a steam system or a boiler system without a flue gas analyzer. In fact, I myself, I would recommend that on top of having units, because you see, these are operational issues. These are operational dynamics. Perhaps it's a high time part of the energy audit recommendation is establishments purchase their own flue gas analyzers to ensure that they always maintain that. Because you see, we are operating these boilers manually. We've never automated them. Yeah. So you operate today, you cannot be guaranteed that it will be operated the same day tomorrow. So as a manager or an energy manager or as the guy on the ground, you will ask him, how do you know that combustion is efficient? That's why today you will see you are consuming too much fuel. Tomorrow you are very efficient. At night you are very you are inefficient. During the day you are not. You are very efficient. Yeah. So let's look at boiler efficiency calculation in steam boilers. There are two parameters here. We are talking about boiler efficiency. That is the steam flow rate, which is normally indicated on the nameplate of the boiler. Then steam enthalpy, and feed water enthalpy. How do you get divided by now the fuel firing rate times gross calorific value? How do you get the steam enthalpy? How do you get the feed water enthalpy? And how do you get fuel firing rate? Steam flow rate, you'll get it from the steam meter. I'm sorry to say most of the establishments also take a shortcut. They don't have a steam meter, but because of the cost associated, they use the condensate meter to assume that that's the same amount of steam, which is not the case. Never use condensate meter to assume that's the same as flow rate. For the reason that steam at 10 bar and condensate at 4 bar do not have the same specific volume. So you'll not get the same flow rate. So if you find an establishment recording those ones, they are lying to themselves. Steam enthalpy, you'll get it from the steam tables. You look at the operating pressure. Let's see if it's a 9 bar. I think the best thing is, let me go to the next slide. No, the steam table was somewhere here. I don't know, I should have put it before here. Yeah, so you see, if you look at the pressure here, say 10 bar. If you look at the pressure here, 10 bar. So you have the enthalpy here, 781. Then if you look at the pressure of 4 bar, which is assumed to be the pressure of the condensate, you have 640. So from there, you could easily calculate the difference in these enthalpies. Firing rates, most organizations do measure the volume of biomass they use. For the tea sector, they use the cuboid, and they record every 30 minutes or every hour, and they tell you I've consumed 1 kilo. So you need to be in a position to understand that what is 1 kilo of 1 cubic of firewood equals to how many kg. From there you'll get your efficiency. Then we have the evaporation ratio. This applies to the boiler as well as the radiators. Yeah. So the boiler will give you, sorry. The boiler quantity of steam generation, then quantity of fuel consumption. This is pretty much direct. You can do it over an hour, it will give you a rate, or you can do it repeatedly until you are in a position to renew. This is so important. In fact, most people would prefer to talk of what is the evaporation ratio of your boiler. Yeah. If you find that this figure is quite high, so you need a baseline. So if you are doing a baseline energy audit, then you need to understand this. So that next time you're coming, you see, are there improvements? Same as boiler efficiency also. But boiler efficiency, the baseline will be the one on the nameplate. So then you'll be in a position to know, are these guys operating the boiler in the wrong way, or they are operating the boiler in the appropriate way. Normally, when you're auditing, especially the boiler, personally, I've seen some energy auditors spend only maybe 1 hour or 2 hours auditing. A boiler, you might have to take something like 5 hours to 6 hours just so that you can pick out all these parameters, because you need to check. And the best time to go is during maintenance day. When you're doing your walkabout, perhaps the best time is you need to ask, when is your maintenance day when they are not processing, when they've opened the boiler for the weekly maintenance. That's when you can open the boiler, you see inside, is there soot accumulated around the fire tubes? Yeah, what is the water quality of the condensate? Are there total dissolved solids? Are they doing blowdowns? Yeah, what's the condition of the furnace? What's the condition of the ID fan? Are there, those are things you cannot see during operation because this thing is closed. Yeah. But if you go there on a Monday, then tomorrow now, the next day on Tuesday, or the day now they are in operation, you would be in a position to now take these measurements and come up with. So you see, in essence, you need to dedicate at least 2 days, even if it means giving maybe 3 hours in a day to check that. Then you go do any other audit or any other measurements. Then tomorrow you come back again to the boiler house, then you check also. So don't just go there for 2 hours. You measure, as Felix, Engineer Felix mentioned, that you only measure the, you do power logging for the FD fan and the ID fan. Then you've already audited the boiler house. The boiler house is a lot. We've not even mentioned the steam system, not yet. Yeah. So these are the heating values for various fuels. These are records you need. They are available online. These are the gross calorific value. Of course, there is a higher heating value. There's the lower heating values. It depends on how you are calculating your efficiencies. If you start with the higher heating values, then throughout your calculation, you need to be using higher heating values. If you start with the lower heating values, then you use the lower heating values throughout your calculation. If you are using the gross calorific value, which is normally the most common, then you use the gross calorific value. Yeah. Then this should be very interesting. This is based on a research done by some university, where they've done fuel, moisture content, and the gross calorific value. So if you look at, say, Greenwood, fuel at 50% moisture content, the calorific value will be 9.5 and not 95. It's 9.5. Yeah. Then green sawdust at 50% is still wood. We are talking about 9.5 also. Seasoned wood, that's now the air dried, the one that has been kept, which is normally the very recommended. So you see, we are talking about a calorific value of 15.5 megajoules per kg. Same as dry sawdust. Wood pellets is the same. Yeah, you could see, and you can see from this trend that the lower the moisture content, the higher the calorific value. These other ones, do you need, as an energy auditor, have you ever recommended, say, to remove the bags? Yeah. What are the calorific value based on that? Normally, those are, you assume it's dry. What do you get out of it? Those are experiments. Those are things that you need to try. I'll share this presentation, but do more research on it. That's the steam table. We are using it to get that. As an energy auditor for steam system, you need to understand how the steam table operates. Of course, there are applications that have been developed by various thermal energy companies like Spirax Sarco and Forbes Marshall, where you only input the pressure, it gives you the temperature readings expected. As I said, if you look at this one at 10 bar, the temperature of steam, and we are talking about saturated steam here, is 180. If you are running that plant at, say, 7 bar, you see the temperature has come down to 170. If you are running at 4 bar, talking about a temperature of 152, yeah. So let's look at tools needed as an energy auditor for auditing steam consumption. I've classified it into two. There are those which are attached to the boiler, and there are some which you walk in to the boiler house with them. And I'll start with the external one. The list is limitless. These are just maybe the bare minimum myself I need to audit plant. Of course, I'm talking about thermal system, not electrical. Electrical, of course, we are talking about you need a power logger here. You need anything else also. So these are specifically to audit a thermal, the steam boiler, as in steam consumption. So a stroboscope or thermometer, as I mentioned, you need to understand one, the ID fan run is designed to run at a specific RPM, perhaps around 1,500, 2,500, so that they can create sufficient draft inside the furnace for stoichiometric combustion. So as an energy auditor, you need to be in a position to get the baseline. What was the design capacity? What was the design RPM for the ID fan? And even the FD fan, what was the design RPM? Is that boiler running at that RPM? The moment you find it's running at a lower RPM, then there's an issue. You look at the root cause now. What is causing it to run at a lower RPM? Are the V-belts loose? Are the V-belt less? You'll find that some guys are comfortable running the ID fan with the 3 V-belts instead of 5 V-belts. Of course, the torque transmission to the impellers will not be sufficient. Or you can check the condition of the ID fan, and believe you me, the impellers inside the ID fan, believe you me, in most cases, when you see a lower RPM, yeah, when you see a lower RPM, believe you me, either it's overloaded, it's jammed inside, the bearings have never been changed or something like that. Then you need the thermal imaging camera for measuring service temperatures. This one is pretty much direct. Normally, even some have applications that can even analyze for you and tell you, just take the picture and indicate for you the temperature. You don't need to record anything. All you have to do is just take notes. Yeah. Then we need the anemometer for measuring airflow speeds, and I should have added here the static pressure and dynamic pressure. Those are very important, especially when you're auditing the fans and when you're auditing the draft inside the boiler. You should be in a position to measure that. Then you need the TDS meter for measuring conductivity in the boiler water. Yeah. the TDS will show you the total dissolved solids inside the boiler. This one affects heat transfer. They become, they observe energy themselves, these total dissolved solids. That's why blowdown is done quite frequency. From there, if you find that the TDS is high, then maybe if they're doing one blowdown per day, then you can recommend 2 or 3. But you also see blowdown is not cost effective. It takes away some energy, but hardly would you find factories doing recovering heat from blowdown water. They actually pump it into the ground and let it go down just with the heat like that. I'll mention something to do with heat recovery from blowdown water. Then what instruments are attached to the steam boiler that can aid you in auditing the steam system? We have the steam meter, then we have the condensate meter. And as I mentioned, never use the condensate meter to assume that that's the same amount of steam you are using, never. Then you have the temperature gauges, then you have the pressure gauges. I think those are the basic ones. With these ones, you can easily give a report and say this boiler is efficient or not efficient. Yeah. Steam meter, as you see when we're calculating the boiler efficiency, we're using the rate of steam generation. Temperature gauges should be in a position to tell you your flue gases, the temperature is high, so there's some there's some heat being lost at the stack. Then the pressure gauges will tell you if your boiler is operating in an optimal capacity. These are the ones needed for energy audit. Of course, there are other attachments. You have the safety valves, you have the Mowbray system. The Mowbray system has what is called an alarm, where in case the water level comes below a certain level, it shuts down the ID fan and cuts out the supply of water to the boiler. Yeah, that's called Mowbray's. Of course, when you are doing an energy audit, you are not only doing an energy audit, perhaps you are doing a maintenance audit. You see, maintenance and energy go hand in hand. Poor maintenance will result in higher energy consumption. So what are the measurements required for boiler efficiency evaluation? Yeah? What measurements do we need? One, flue gas analysis. And this one, you use the flue gas analyzer. The flue gas analyzer will give you, these are the main things that you need to look at as an energy auditor. The percentage of CO2 and percentage of oxygen in flue gases. Then also the flue gas analyzer will also give you the amount in percentage of carbon monoxide. And as you see, anything above 400 parts per minute tells you that unachoma makaa, or your combustion is not stoichiometric. And as we said earlier, the higher the CO2, the better the combustion. Of course, higher levels of oxygen means you are not utilizing the oxygen supplied into the furnace. So some of it is escaping. And they are not escaping only, they are also going away with the heat. Yeah. Then you need flow measurements for fuel if you are using HFO. Steam, of course, you need the steam meter. And most organizations are reluctant to install the steam meter. But those are recommendations you need to do. You need to find out how much a steam meter is and give them the cost-benefit analysis of that. Then you have the feed water. You need to measure flow measurements for the feed water. Normally, there's a standard meter for that. Then the condensate water, you need to measure so that you compare how much water you are using. Because you see, the moment you are using, you are finding yourself replacing a lot of water in makeup water. Then you say makeup water. Then there's a problem in your steam line. Either your steam is leaking somewhere or the condensate is leaking somewhere. Yeah. And that's not good, because if steam is leaking, that's live energy going. If condensate is leaking, also that's some amount of energy. And also you're also losing treated water. I'll give the advantages of why condensate recovery is very key. Then you need to measure the rate of combustion air generation. Of course, these ones you'd measure using the anemometer inside the stack. Then you need temperature measurements, one for flue gas, steam, even though if you have pressure, then you will easily determine the temperature for steam. Then you need temperature for makeup water. Normally it's ambient, but it's good to record. You also need temperature for condensate return. This is critical as an energy auditor. Why? Temperature for condensate return should not go beyond something like 85. 85, maybe 86 there. But the moment you start hitting 90, then this is already starting to transform into steam. The latent heat of vaporization is already transforming into steam. High condensate temperatures means there's some steam leaking into the condensate line. So you are losing steam instead of utilizing steam. So you need to do a root cause. Where is the leakage happening? Are there steam traps that are failed? Of course, I'll mention how to check the operational, efficient operation of steam traps. Yeah. Temperature measurements for combustion air. As I said, higher temperature measurements for combustion air means you're also losing energy. What's the temperature for fuel? There's for this basically for HFO. Then boiler feed water temperature also. This one should also not go beyond 80. If from your condensate tank, you need to be supplying this water at around 80. You see, the feed pumps are designed not to operate as steam pumps. They are designed to operate as condensate pumps. So the higher, by the time your temperature reaches 100 and you are pumping that water into the, you will kill that pump. And subsequently, you might end up killing your whole boiler. Yeah. So you are still measuring on measurements. So you need to take measurements also for steam, and pressure measurements for steam, fuel, then pressure measurements for combustion air, both primary and secondary. Combustion, that's inlet and outlet. These you use the anemometer, because anemometer will give you the static pressure at the inlet of the furnace. You just place it there, it will just give you the pressure reading. Then at the end, you might have to insert a probe so that it gives you the pressure readings. There you can easily determine the pressure drop across the furnace and determine. Normally also the boiler nameplate will specify the pressure drop across the furnace. So what is the water condition? You need to be in a position to measure the total dissolved solids using the TDS meter. These are things that a factory or any establishment should have. Then the pH of the water, of course, it shouldn't change if you have a closed loop system. You're just monitoring that nothing is changing. Then the blowdown rate and quantity. There's something that I need to mention here. If you look at most establishments, you find that many of them do not treat the water, makeup water that is supplied into the boiler. They assumed that the chemical treatment of water that you add into the condensate, that online feed should be sufficient. But while at the same time, you'll find some establishments have actually installed reverse osmosis plants in the boiler house just to treat the water that goes into the makeup water, which is recommended. Because if you look at the cost benefit of treating that water, you will reduce the rate of blowdown. And you see the rate of blowdown. If you do 3 blowdowns, you are talking about either 6 to 7 cubic meters of firewood. Yeah. So if you reduce it to 1 or even none, because you've treated your water, then it's close looped, then it might be good to go and save a lot of energy. Yeah. Those are recommendations you need to make. Basically, this is an example. I think I'll leave it to you of calculation of efficiency in steam boilers. Yeah. Basically, it has to do with, that's the formula I've just shown. That is the flow rate, then the enthalpy change. These ones you'll get it from the steam table. Then the quantity of fuel, then the gross calorific value. Basically, it's just a calculation of that. Yeah, it's pretty much direct. You should be in a position to, even during audit, to come out and say your boiler is not efficient. Adjust ABCD. Yeah. So what are the energy saving opportunities in boilers? Yeah, there are around 6, 7. What can you do to the stack temperature? What can happen to the excess air control? What can happen if you preheat combustion air? What can happen if you preheat feed water? What do you do with the radiation losses? What do you do with the blowdown losses? And what do you do with condensate recovery? Remember, I mentioned condensate. Yeah. So stack temperature, as I mentioned, that high temperatures at the flue gases signifies that some heat is being taken away from the furnace, which should have been transferred to the boiler. Basically, the recommended temperatures should be between 135 and 250. 135 and 250. Okay, it depends on the pressure rating for the boiler, but specifically for a 10 bar boiler, a boiler designed to operate at 10 bar, then 135 is comfortable. But if you are talking about a 250, not 250, you are talking about a 20 bar boiler, then 250 will be okay. Yeah. And from experience also, because I've done quite below, Monday is a maintenance day. Tuesday, you'll find that the temperature reading is 135. Wednesday, the temperature reading goes to 140. Thursday, the temperature reading goes to 160. Friday, the temperature goes to 180. Saturday, the temperature is at 200. Then Sunday, the temperature is at 250. That is not recommended. You find that the temperature goes up. So you need to find out why the temperature is going up throughout the week. It's because of the soot that accumulates inside the fire tubes. Yeah. So those ones during Monday cleaning, ensure those are cleaned. You should check if they don't clean. Some guys just leave it there. Yeah. So what do you do with excess air control? Because as I told you, excess air means incomplete combustion. Yeah. So supply of excess air to the steam boiler should be avoided at all costs. O2 levels at outlet of boilers on a higher side would mean heat losses due to excess air and dry flue gases. What are the remedies? As I said, maybe you need to install an online flue gas analyzer, not necessarily oxygen, so that you can get the two. Then install a variable frequency drive or a VSD on the ID and FD. I believe if you've attended CEM or if you've been an energy auditor, VFD should not be. Maybe for the sake of those who've never interacted with it, VFD is a variable frequency drive, and VSD is a variable speed drive. Both of them serve to achieve the same thing, control the speed of rotation of the fans. The other one is for the DC, the other one can be both for the DC, that's the VFD, and be both for the DC and AC. Yeah. Then operate, the other recommendation that's for controlling excess air is operate the FD fan with O2 levels as feedback. That's when you're talking about the VFD. Then ID to be operated with furnace. That is, okay, I should have finished this one. The ID fan should be operated like, if you open the furnace door, the ID fan should shut down. You get what I mean? You put a switch so that when you open the furnace door, the ID fan cuts out immediately. Then when you close, it just comes back. Basically, that's what it means. Then the other strategy for boiler efficiency, we are talking about combustion air preheating. You must have heard now, we are talking about air preheater. That is installing an air preheater and a properly sized ID fan will help overcome reduction in pressure drop. You find that the temperatures of the flue gases can be utilized to preheat the air, as shown in this diagram, to preheat the air that goes into the furnace. You find that cold air comes in, then on a right angle flow, flue gases come in here. This is sort of a heat exchanger. So the cold air picks hot air, the flue gases gives out heat, then it goes out with temperature. And you've seen temperatures coming here at 23, leaving it here at around 70. So you see that's a lot of efficiency savings in terms of fuel consumption. Yeah, but now there's a challenge. Once you introduce this, then you bring in the issue of pressure drop. You reduce the pressure drop, so there isn't sufficient draft, and that's why something called a forced draft fan is introduced. Sorry, a forced draft. That's why you hear of FD fan is introduced. There are three types of air preheaters. We have tubular type, plate type, and storage type. Then we have the economizer. Economizer works on the same principle as the air preheater. The only thing is that now it's the water, feed water, which is being preheated. Yeah. Normally, you find that the feed water can be preheated up to temperatures around 95 to maybe 98, just before it converts into steam. But normally, when you're installing, so what happens here is that the inlet gases also flow, counterflow. The inlet water, feed water, does counterflow with the flue gases picking up heat. So the temperature of the water here leaving should leave at around from, say, if the condensate was around 80, which is normally the practice, then you'll find that the water leaving here is around 95. You've already preheat, so the boiler will have less work to heat that water to, say, 150 to 160. So you use less fuel. Basically, that's what it means. But you need special equipment here. Once you install this, then you need a special pump that can now be used to pump. You are not going to use the ordinary feed pump. That one will just blow out if you use that. And that's why you need to keep an eye on this temperature if you are not using that. In my own experience, an economizer is more effective than an air preheater. Yeah, why? An air preheater will reduce the pressure drop. You don't create sufficient drop. Then you don't achieve effective stoichiometric combustion. But you see, this one doesn't affect combustion. You are actually assisting the boiler. Yeah. The only thing is the ID fan has to do more work pumping out the water, which is normally with a good ID fan, it should pump out the flue gases effectively, even though you might have to increase the sizing or you create some draft up there. Yeah. Then here we are talking the next energy saving opportunities. I don't have to mention much about this. We are talking about insulation to minimize radiation losses. Yeah. Normally, when you go to a boiler house, these are typical, and I took it one time. When you go to a boiler house, this is what happens at the end plates mostly, which is normally very much neglected. The shell itself is well insulated, but the end plates are not normal. And the reason why the end plates, you lose a lot of heat there, is that they are not insulated from outside, but they are insulated from inside using refractory bricks. Yeah. So normally over time, these refractory bricks fall off because you see these acts like you see the flame comes and hit it, then reverses. So kind of over time it falls off. So that's why it's important when you are visiting a factory, you go there when, or an establishment, you say a factory. When you are visiting an establishment, you go there during maintenance. You can ask for this place to be open and check the refractory books. This one is an image that you're playing using the thermal imaging camera. Yeah, there are several in the market, and they're not quite expensive. Yeah, so you should be in a position to calculate this temperature and the surface area. Then you know how much it is lost here. Then we have energy saving opportunities still. We have blow down water recovery. As you know, when you are doing blow down, you are blowing out live steam. Yeah, you are blowing out live steam, and that goes on with energy. So the more the blow downs, the more energy you lose. Yeah. So, but there is a way of doing it. I know you can use a flash vessel. Basically, these are flash vessels. So flash vessels are not only in dryers. I'm sure for many of you visited tea factories, tea processing factories, you've seen a flash vessel attached to the dryer. You've never, most probably you've never seen a flash vessel attached to the blow down pipe of the boiler. This one can be attached to the boiler. Of course, flash vessel is kind of an expansion chamber. You supply steam at high pressure, then you expand it. During that expansion, some flash steam is generated. That flash steam carries a lot of heat energy that can be recovered and used in the process. Normally, because of the travel of flash steam, the flow rate is low. For this one, it works very well, especially for flash steam, for the blow down flash steam recovery. It works very well when you have a dehydrator that utilizes a bit of steam to actuate the dehydration process. So where you find a dehydrator, you'll find a flash steam. Then we have the condensate recovery. Remember, I promised you that we'll mention something to do with condensate recovery. Of course, condensate recovery carries a lot of heat because we are talking about temperatures of 85, 80, then it flows back. So condensate recovery is so critical because you don't lose a lot of heat. You actually save the boiler from firing, say from ambient condition to that. I'll mention the advantages of condensate recovery, but let me mention first the components of a condensate recovery system. The moment I mention about condensate recovery system, what you need first is a condensate tank. Yeah. Then I think let me mention how the flow happens. So let's start here. The condensate steam enters the plant. In this case, it could be the radiator, it could be the dryer, it could be the calorifier or anything. Then the condensate flows into a condensate receiver, which is in the boiler house. It's something that looks like a header. So the condensate receiver is located in a pit alongside this one. This is an Ogden pump. The Ogden pump is actuated by steam at low pressure. Normally, this low pressure steam is operating at 2 bar. That actuates uses the ball cock, which floats as a result of the steam being flushed into the condensate tank. Basically, the mode of operation for this is like a hydram. Yeah, sort of. But now you see hydram is operating on cold water. So the condensate pump, which is normally called the Ogden, pumps the water into the condensate tank. Then from the condensate tank, it goes back to the feed pump. This is a mechanical pump. It doesn't use any energy. It only uses motive steam at 2 bar. Some establishments have electric pump. Then you don't need a pit. Yeah, you don't need a pit. Everything is on the surface. Yeah. So whenever you visit here, you hear something knocking, ka-chang, ka-chang, ka-chang. That's the condensate pump. It's called a mechanical pump. And it's the most common one because you don't use a lot of electricity. It's easy to maintain. And normally this pump has a meter. So whenever you visit an establishment and you want to know how much condensate is generated, this pump has a meter located somewhere here, just before this valve. So in a count, it has a counter. So you should be in a position to record that, take the time, zunguka, come and record, get the hours, get the amount of condensate generated. There you have your record. Yeah. So what then we have a deaerator. That's still energy saving strategies in a boiler house. Sorry, I missed out the T here. The purpose of the deaerator is to reduce dissolved gases, particularly oxygen. Oxygen is not required inside the steam. It's one of the primary agents for corrosion. Yeah, and that's why you have air vents throughout the steam system. So oxygen should be kept to a low level to improve the plant's thermal efficiency by raising the water temperature. In addition, the aerators provide feed water storage and proper suction conditions for boiler feed water pumps. I don't have to say much of that. So what are the reasons for condensate recovery? Yeah, one is that, you see, you don't have to spend a lot of money purchasing water. If you assume a place, so let me give you a good example. Most meat manufacturing companies use open loop steam system. Yeah. So you can imagine the amount of water they use inside the boiler and how much they are paying. We are in Nairobi, they are paying water bills. Yeah. Condensate recovery reduces water charges. Even can check, I think, those meat processing factories. Pharmaceutical companies is the same thing, they use open loop. So, and you see, this is treated water, you pass through reverse osmosis and everything. Yeah. Then you have fuel costs are reduced. No, effluent charges. Now, the moment you are talking about discharging water, municipal will come and tell you, yeah, you've consumed this cubic and it has gone to waste. So the effluent charges is associated with how much you consume. So it goes up also. Then fuel cost charges are reduced because you see the condensate is returning to the boiler at around 80, 85 degrees. So you don't have to preheat it from 23 or ambient temperatures to 80. And imagine that difference. Then more steam can be produced for the boiler, which is normal. And boiler blowdown is reduced because you see, this is water that you've treated. So you are not introducing any impurities into the boiler. So you reduce blowdown and therefore you avoid losing energy through blowdown. Then we have chemical treatment of raw makeup water is also reduced. So if you have a perfect closed loop, you might not even need the chemical treatment of water. Yeah. So what are other operational energy saving measures in steam boilers? As I mentioned, you need to reduce the frequency of opening the boiler furnace door to avoid cold air being sucked into the air. Perhaps you need to sit down at the boiler house and see how frequent the boiler operators operate. Some guys even leave it open, they just throw in firewood, throw it continuously without closing that furnace. Tell me of the efficiency, how it will come out. And another way of doing it to avoid that is use sensor switch that shuts down the ID and FD fan when the boiler door is open. And I can tell you at the end of this presentation, I'll show you how improvement in efficiency this has helped one of the factories here in Kenya. Yeah. Then use biomass with low moisture content. Then maintain appropriate water level inside the boiler. I mentioned, I think I spent a lot of time mentioning how the water level inside the boiler makes it effective. High water level means you are going to accumulate less steel, then you are going to be firing that boiler continuously. So you need space inside the boiler to accumulate steam. And set the correct airflow to achieve stoichiometric combustion. This is just operational issues. And you descale the water side of the boiler by using appropriate water treatment chemicals. Then undertaking regular blowdown to reduce the amount of TDS. That is, if you are using an open loop system, but blowdown should be avoided at all costs. But TDS is also costly if you let it reside in the boiler. One time you'll open it and you'll find a whole mudslide. I don't know if you can ask anything to do with steam boilers before I go into the steam distribution system, or I proceed.
Engineer Mangerere has a question.
Yeah, please.
Hello, Engineer Lagat.
Hello, Engineer Mangerere.
Hopefully, we have met somewhere.
We've met quite often. I was your
Yes.
student at one point.
Yeah. Okay. Now, you have talked about controlling the percentage of oxygen in the
Yes.
flue gas as a
Yes.
measure to improve energy efficiency or boiler efficiency.
Yes.
And I agree with you. Now,
Yes,
the common
sir.
practice is to have 4%, 3 to 4%
Mhm.
oxygen in the flue gas for
Yes.
for fossil fuel fired boilers,
Yes.
IDO HFO. But
Yes.
for biomass fired boilers, empirical
Mm-hmm.
data indicates that if you want to achieve the 40% excess air, which is recommended for complete combustion, then you need about 7.5 to 8% of oxygen in the flue gas.
Yes.
And I mean, of oxygen in the flue gas. And this is controlled by the volume damper on the ID fan, or if
Yes.
you have a variable speed drive, you
Yeah.
can use the variable speed drive to
Yeah.
control the speed of the ID fan. Those are my comments.
Yeah, that you're absolutely right. I think we've brought in very critical parameters. I thought because it varies from energy, from the kind of fuel to kind of fuel, I didn't want to mention it here, but I think it's you are right, Engineer Mangerere.
Thank you very much for the good presentation.
Yeah, thank you so much for your input. Okay, may I proceed? Or anyone else?
Yes, please, engineer. You can proceed. I've not seen any other person asking a question.
All right, thank you so much. So let's look at the components of a steam distribution system. Yeah, and what you have on the screen is basically what you would see throughout a steam distribution system. What you have here is the supply line from the steam boiler. And then you have your separator. When you talk about separator, we are talking about water separator. You remember when we talked of the levels of, when we talk of the level of water in a steam boiler, I should have mentioned that a high level of water in the steam boiler also, apart from reducing the amount of space that you use to accumulate steam, you'll also have a lot of carryover along your steam line. Of course, that notwithstanding, still, if you even have the appropriate level, then you still carry over some water into the steam line, which is not recommended. One, is not recommended because there will be those issues of water hammer, there will be issues of corrosion, of course, and it will affect the steam generation and pressure capacity of the boiler. So the separator serves to remove any water from the steam line, steam supply line. And you can see here, they've installed a trap set. This is called a trap set, yeah, or a steam trap system. So once you remove that water, then the steam can now go into the plant. Let me mention something to do with the steam trap system here. And I think you need to really familiarize yourself here, because there's normally a lot of confusion on how this is installed, and poor installation of this one might make your trap system not functional. Yeah. So what we have here is the isolation valve for isolating the trap set when you want to service it. You have both here and at the end here. Then the next one, you have a strainer. Now that you have liquid here flowing, of course, we talked of the water is not pure, corrosion and everything. You have stuff here. So then you have a strainer. A strainer serves to remove any impurities in your condensate, because you see the steam trap operates on very small orifices, and if it's blocked, it makes it ineffective. Yeah. So the strainer here traps, and it has a cork here that can be opened on a regular basis for cleaning. So even as an energy auditor, when you're auditing that, you might ask the plant operators to open here and check the strainer if it's clean. You might be surprised even some have removed the strainer so that they don't block the steam, the condensate from flowing. Then what you have here is a sight glass for inspecting the effectiveness of the steam. We are talking about these are Spirax circle steam traps. Some don't have, some do have, but this is mainly for checking. It has a port where you can connect an inspection gadget called the Spiratech. But in the absence of that, you can use a thermal imaging camera. Then this is the steam trap itself that prevents the steam from going into the condensate line. Then here you have a non-return valve. You have a non-return valve. The non-return valve prevents condensate from coming back into the steam trap. You need to check functionality of this and how it's installed. You'll be surprised sometimes this one is installed in the reverse. Then it blocks everything, it doesn't go ahead. And this is the isolation valve. So this is available online. Even if you are stuck somewhere, you are suspecting something, just check trap set setup. You'll easily get it. Now let's go down. What we have here is by practice, it's always good to supply steam. It's always good to supply steam at high pressure to the point of use. Then now when going into the actual plant, you reduce the pressure of steam. What do you use to reduce the pressure of steam? You use a pressure reducing station or a pressure reducing valve, because unless the plant is designed to operate at the boiler pressure, that's when you don't need the pressure reducing station. You only have to supply that plant at 10 bar. And a good example is, say, dryers at KTD or tea manufacturing factories. You'll find that those dryers are designed to operate at 10 bar. Yeah. So you wouldn't see a pressure reducing station. But if you go to smaller plants, like say the withering traps, then you'll realize that they operate at 4 bar, that pressure. Yeah. Then, so you have to use a pressure reducing station to reduce the pressure to 4 bar, then you now supply. If you find that someone, you know what happens in most practice and in most establishments, I've seen it in the meat factory, I've seen it in a chocolate factory and also tea factory, some tea factories to be exact, is that instead of using a pressure reducing valve, they just throttle, which you experts here can agree that you never throttle steam, because you'll not reduce pressure. You'll still be, then you'll find that you're scorching or you are overfiring your plant, because you see, when you look at the steam tables, steam pressure at 10 bar, temperature at 10 bar, and temperature at 4 bar are totally different. Yeah. Some even you might operate at 2 bar. Say if you are doing what do you call culturing? If you are culturing, say in a meat factory, you need around 60 degrees Celsius, or if say you are withering, you need to wither at around 65 degrees Celsius. You need to drop down that pressure to appropriate pressure, but you cannot do throttling. So pressure reducing station serves to do that. So basically, this is the setup of a steam system. The length can vary. Yeah. And also one more thing is that an effective steam system should always have these separators at several places. It's not only one. Yeah. And normally this separator is put just before the plant. Say if you have a dryer, you just put it just before the plant. If you have, say, an autoclave, you just put it there so that water doesn't go into the plant or the use of, or the radiator for that matter. Yeah. So the other thing that you need to know about steam distribution is that steam is distributed at high pressure, as I mentioned. This leads to reduction in piping costs and distribution losses. An increase in steam pressure decreases its specific volumes, enabling use of smaller pipes. I think that's self-explanatory. The volume of steam decreases with an increased pressure, making it possible to carry same mass of steam through pipes at last. That's why I was explaining. You carry steam at high pressure to the nearest point, then now you can reduce it. But you cannot reduce it at the boiler house and supply, say, 50 to 60 meters away. That's not effective. So that's what I was just trying to explain. The use of lower bore sizes will bring in significant difference on a day-to-day operation by reducing radiation losses and lower material cost. And I said at high pressure, you can use lower bore, lower diameter steam pipes. Then you reduce the cost of it, or the capital cost of installing those, the steam system. Additionally, distributing steam at high pressure facilitates use of small compact pipes. Yeah. Then again, distributing steam at 8 bar instead of 4 bar saves 20% in piping cost. You can see the savings. Yeah. So what are the features of efficient steam piping? Shortest possible distance. Of course, you cannot transmit steam 100 meters away, but if need be, depending on the size of the plant, take it at high pressure, then pressure reduce it, then distribute it. Yeah. Then proper draining or condensate. Yeah. You need drain points at every 30 to 40 meters. Then proper slope of the condensator. Yeah, that is 125 for every 30 meters. Then branch lines to users should be connected at the top, not at the bottom. That one will be discharging water or condensate or carry over water into the plant. Then proper support to avoid sagging, because sagging will create pits for accumulation of water. Then proper expansion loops, I'll demonstrate that. Then minimum pipe redundancy. So let's look at steam traps. And as I explained, the function of steam traps is to prevent steam escaping into the condensate line, thereby avoiding energy loss. So how do you evaluate a steam trap? Yeah, a steam trap, basically with a thermal imaging camera, at the upstream, let me say upstream, where the steam is coming from, the temperature should be high, perhaps at the same pressure. If the pressure is 8 or 10 bar, then you should be getting the temperature reading of 180. Then on the lower side, after the plant, that is after the steam trap, then it should read something like the condensate temperature. So we are talking about 90, 80 to 70. If you see such a feature, then it means your steam trap is effective. But if you read here 180 and here is 180, then you are passing light stream down and you are losing energy. Yeah. you're actually supplying steam to the condensate line. Basically, that's how to operate. Of course, there are other methods of of checking steam traps. Yeah, I mean, you can use a stethoscope. You can use Spiratech. Stethoscope will give you the noise if there are vibrations. You see, steam tends to do a lot of vibration. There are special equipment for doing that. Spiratech, if you have Spirat Circle steam traps, will tell you, will give you a green light if the steam is not passing, a red light if the steam is passing. Basically, that's how to evaluate. And you can see a mount here. So this is the correct way of installing steam traps. This is a set of radiators or a radiator battery or bank. Yeah. And you can see these are 3 radiator banks. Most establishments, you'll find that they discharge condensate into one steam trap. Yeah. Then this is not effective because you see, if the fan is blowing from this side and this side, the rate of condensate generation from here to this middle one and this one are totally different. Yeah. This one will perhaps generate more condensate. And you see, steam traps are normally sized based on the pressure and the flow rate which steam and condensate is being generated. So you cannot use 3 radiators to do one. This is common, especially in tea manufacturing factories, especially some funny dryers called VFBD, vibratory fluidized-based dryers. Those ones, you'll find most of those Indian manufacturers, they've done this. But the best way to do is this one. Each radiator bank will have its own steam trap. Still on steam traps, yeah, you see, when you are tapping the steam trap, say from a common header, you use the same pipe diameter to tap, not a smaller pipe diameter. Then from here, you can easily pick, then it just flows into the trap set, and then the trapping is done. I think that's self-explanatory. Then going to insulation, of course, insulation, I cannot underscore the importance of insulation in steam system, especially distribution. Yeah, because any exposed surface will mean direct heat loss, and therefore you lose on heat. Types of insulation, you have glass wool, you have calcium silicate, and you have cladding sheets. There are cladding sheets special covering open surfaces. Of course, insulation leads to higher heat losses. And you can see here, heat losses at different surface temperatures. Yeah. If a surface is exposed. Yeah. So this is the amount of heat. If your temperature is reading that, you are losing 500 kilocalories per whatever. And if it's reading 100, then you are losing 1.3 megacalories per meter square. You should be in a position to estimate the area and calculate the amount of heat loss, same for 200 and 400. So, and what are the economic thicknesses of insulation? You see, there is a level beyond which if you insulate, then it becomes a point of no return. You are not getting any investment. So the cost of increase in thickness of it should justify sheer savings. Beyond certain value, further increase is not economical. The concept of economic thickness of insulation. This graph explains that. Yeah. There is a level beyond which if you increase insulation, then you are not going to get any benefit out of it. Steam leakages. How does it happen? Yeah. This is so critical also, and most probably when you are going to factories, you've seen a lot of steam leakages, and normally it happens through valve passing. I'll demonstrate that through flanges, through faulty traps, through valve glands, and through material deterioration. Of course, steam leakages lead to direct loss of steam and is costly for any establishment. And This happens as a result of wear and tear of gaskets, fittings. You know, steam is an active thing, so there's a bit of vibration, and over time, there's fatigue of equipment. The location of steam leaks are commonly found in pipe fittings, valves, steam traps. So how do you prevent leakages? Say at the flanges, instead of just coupling directly the flanges, then use an expansion joint that observes the shock, so you don't transmit that force into the flange or the gasket, thereby lengthen the life of the gudgeon. It's as basic as that. We have leakages from valves, yeah, and you can see that you'll find that steam coming out of here. So interior leakages inside valves happen on the valve seat. So normally there are kits to service these valves. So normally, if you start realizing that there are leakages there, then ensure you have planned for preventive maintenance. Of course, now as an energy auditor, you're supposed to find out how much does a valve cost and how much steam is being used from that area. You can estimate. Then steam traps. Also, these are leakages from steam traps. The steam trap can fail in an open mode because of debris or whatever, or the steam trap can fail in a closed, permanently blocking the flow of water and steam downstream the condensate line. What happens is that now you'll find it bursting the gaskets and the leakages happen. So whenever you see a leakage, follow up to the trap and see if there are leakages inside the trap. If the traps fails in an open position, then you should be in a position to pick out that you should be in a position to pick out that using the thermal imaging camera, where you'll find that the temperature upstream and the temperature downstream is the same. On your right here, I just wanted to mention that these are two types of stream trap. Of course, these are float stream trap, and we have an orifice multi-stage stream trap. This one, the first one, float stream trap, normally requires a lot of maintenance. While orifice is new in the market, I think it's now around 5 or 6 years, but there's a lot of resistance to its adoption. But it's quite effective also, especially when it comes to saving on steam losses. What I need to tell you is that the float steam trap does not permanently prevent steam losses downstream in the condensate line. There's some steam that passes, however, in small quantities. Of course, I hope Spirit Circle will not come after my guns, after my neck. Well, this is an orifice steam trap. There are no mechanical moving parts. The only thing which is moving is the strainer. Yeah, for which if it blocks now and you block the orifice, then you'll realize that the gasket starts leaking. Yeah. So that's basically what happens down the steam distribution lines and how energy can be lost there. Let's go to end use, plants and equipment and steam consumption. So auditing energy consumption for steam in an establishment requires one to understand how steam is utilized. As an energy auditor, you need to understand how steam is utilized. Is it utilized for drying? Is it utilized for cooking? Is it utilized for sterilization? Yeah. Is it utilized for motive steam or power, as I mentioned in the introduction? So to audit energy consumption in end-use equipment like dryers, calorifiers, turbine cookers, and autoclaves, one need to appreciate the following. One, if you are talking about, let me talk about a dryer. Okay, it can be a dryer, pasteurizer, or whatever. you need to understand the production capacity, how much that is producing. And these records must be kept. If you are auditing any plant, you must ask for this record. What are your production records? If they don't have, then you might have to measure. If, say, you are producing powder, then you get a bucket and measure the throughput of that. And you repeat it 3 or 4 times. By that time, you measure for 1 minute, then you prorate it for 1 hour, then you measure for 1 minute, you measure for 1 minute, wait, then you prorate it for 1 hour. You'll be in a position to, even if it's a quarry, okay, no steam in quarry, of course, but if it's a quarry, you can do that. Same as for liters, yeah, how much per hour does it produce, yeah, if it's juice or whatever. Then you need to measure steam consumption rate, kilograms per hour or tons per hour, yeah. If they don't have perhaps a steam meter, part of the recommendation that you need to do is for them to install a steam meter along the steam supply line. Some organizations have even gone to an extent of installing a steam meter in each and every plant. That is, dryer 1 has its own steam meter. Dryer 2 has its own steam meter. Yeah. Because say, if I buy a dryer, say from McCloy or Marshall Fowler, and they tell me this dryer consumes steam at 1,800 kilograms. Okay, that's how they normally say, 1,800 kilograms of steam per hour. Then when you try firing that steam dryer with your 10 bar steam at 4,000, you still find the dryer is struggling, you're not achieving the temperatures. So why you told the truth? It could be that this guy reduced the number of radiators, so you're not achieving the sufficient firing capacity of the dryer. Or it could be put excess radiators, that's why it's consuming more steam than it can fire. Yeah. Then you need to understand the operating pressure. This one is available along the line. Then operating temperature. What is the operating temperature of, say, the dryer, of the calorifier, of the turbine, cookers, autoclaves, and everything? Having the above information at hand will enable the auditor to evaluate the efficiency of the plants in terms of, 1, actual capacity versus the desired production capacity. So say you've measured a dryer and you realize it's doing 400 kilograms of, say, made tea per hour instead of 600. Obviously, that dryer is operating below capacity. Yet you are generating steam at 1,800, which is meant to produce 600. So you can see that you are wasting steam. You are producing steam that is not being utilized fully to produce the desired amount of tea, yeah, or powder for that matter. So you also need to understand the amount of steam produced per kilogram of products. You see, once you have the amount of kilograms and you say 1,800 per hour and you are producing 600, so you should be in a position to say 1 kilogram of steam will give me 200 kilograms of powder or made tea. You see, there now you need to present that in your report and tell the client, if we take these measures, your production will go up to 300 kilograms of made tea per kilogram of steam. You see there, that will be direct cost saving. Then what are the operating temperatures versus the design temperatures? Are you achieving enough firing capacity? These are to do with firing. So it talks about the quality of products. If you don't fire sufficiently, then the firing will not happen also. So any establishment ought to keep the above record on a daily basis and put in place procedures to track the trends on a weekly, monthly, and annual basis. Then you can easily compare. Even last year we were doing ABCD. This year we are on an improvement track. If not, again, these records are not there. As an energy auditor, you should be in a position to now give a template and tell these guys do ABCD. Then next year you will be in a position to track and say, yeah, we monitor this and this is now the production. You see, you now start working on continuous improvement with the client. So whenever you find something is not happening and it should happen, put it in the report and make recommendations so that you can track those parameters. Yeah. So anything falling short of the design capacity, call for a thorough investigation to identify the root cause and make appropriate recommendations. This is just two different factories. I'll not mention the name for the sake of privacy. And they are in, all of them are in Kenya. Perhaps they are even in the same region. But this is the firewood consumption. Normally they track firewood consumption like in terms of kilogram made tea per cubic meter of firewood. Yeah. So the first factory, and it was repeated across all the factories. I just picked a sample. These guys have around 6 factories. I just picked a sample, one of the factories, but the trend was the same. If you look at 2018, these guys were producing 582 kilograms of made tea per cubic meter. What should interest you is in 2019, these guys were producing 700. I'm assuming this is 800. I'm sure Engineer Mangerere and Phoenix and Njeru should be surprised to see this. They were doing 700, 739. You can see the trend. While on this other one, these guys have only been doing on average 270, 300, 240, the average in 260. So you guys can see the trend. And if you see the setup here, this factory, one, they had all this, what I've just discussed. They had an economizer, a deaerator, limit switch for opening the boiler switch. Then they retrofitted the dryers to increase the number of radiator banks so that they fully utilize the amount of steam generated in the boiler, what I was just saying. So as you can see, majority of the factories in Kenya lie here. Worse, even the private factories, leave alone the tea estates. The private factories, I can tell you, they are doing worse than this. They are doing up to something like 180, 200. It's not a good picture to say. But you see some private factories, and this one I singled them out. These guys are still doing the same. Even as I talked to them yesterday, they were still doing the same. The only thing is they could not allow me to take pictures of how their setup is because of privacy, I guess. It's, yeah. So basically, perhaps this is how you need to track the firewood consumption. If you have several factories or one factory, then you can easily track the energy intensity. As you can see this table, one here we have the made tea, amount of tea produced. That's for the month. We're talking about a month, not here. Amount of tea produced. Then we have the quantity of firewood consumed. Then you have the metric now, the kilogram of made tea per cubic. Then these are comparatives. Then you can go ahead even and do the cost. How much are you using per kilogram of made tea based on the firewood consumed? You see, when you have these metrics and you can easily calculate these metrics for a factory, they will easily now appreciate your recommendations and implement them. Yeah, so record keeping should be very critical, and I cannot overemphasize record keeping. In conclusion, so when auditing the steam system in an establishment, the overall objective is to understand the setup of the steam system, whether it's open loop or closed loop. Obviously, efficiency in open loop is quite low since there are no condensate recovery. There is no condensate recovery. The rate of fuel use, as I mentioned above, those ones need to be tracked. It should be a record. Yeah. Then the production capacity of the plant. You should be in a position to know what's the total production capacity of this plant. Of course, lastly, auditing steam systems require a lot of observation and judgment. I've attached a checklist. I don't know if I'll share or will ask a question. Can I? Will ask questions before I share the checklist, because the checklist is just a guide.
Okay, engineer, are you done?
Yeah, I'm done. Yes.
Okay, fine. We welcome questions, comments, clarifications, additions, criticisms from the presentation engineers presented for 2 hours and around 10 minutes. Oh, we start with the Eustace. Yes, Eustace.
Yeah, we have just
Thanks, Engineer Lagate. That was quite good and good explanation of our boiler performance. Though it could have been better if explained the relationship now between the boiler and the steam system. All in all, I just wanted to add something a little. When you are auditing a boiler after you have assessed the boiler performance itself, the steam systems on itself, as an auditor, you should now try to assess the whole system as a whole. If you look, Engineer Lagat.
Yes, sir. Yes, sir.
Can you go to the place where you have shown the equation for the steam fuel efficiency?
This one. Oh,
Yeah,
this one.
there. Yeah. The reason why I am stressing on auditors, when you are auditing, please, after you have assessed the boiler steam system in parts, you have assessed the condensate, you have assessed the steam traps, you have assessed the combustion efficiency and so on. The boiler steam fuel efficiency is the last resort to show the performance of the whole boiler steam system. Because if you look at it clearly, if Q indicates the steam generated per hour, and you find boilers are rated, say like 10 tons, that is, or 6,000 kilograms per hour, or 10,000 kilograms per hour, or 8,000 kilograms per hour, as in this case. In this case, for example, if the boiler is not utilized to almost full capacity, which we emphasize it should be more than 80%, you find now Q will be very small, meaning the efficiency of the whole system will be very small. So it is also good to establish whether the boiler is optimally being utilized to the full capacity. I think that's my comment. I hope it has been understood.
Yeah. I think that's quite in order, Engineer Njiru. Yeah.
So exactly what I meant is make sure that Q is as near as possible to the specification of the boiler.
To the boiler rating.
Or else, yeah, the boiler rating. Or else, if most of the time they are operating like, say, half of the time, it's better to recommend you should have either a smaller boiler and a big boiler.
Yeah, and I think to add on that, Eustace, is that, as I said, most establishments have not installed a steam meter. So that's why they cannot easily pick out Q. And you see, the moment you don't have a way of determining Q, then you really struggle to determine your boiler efficiency. So maybe as a recommendation, further to what you've just said, is perhaps as energy auditors, part of the recommendation you need to do is first install a steam meter. Even if it's a master meter at the boiler house, the one that supplies the header.
Yeah, in fact, there is a auditor on some facilities in some countries. Steam meters is a compulsory. Steam and the fuel meters is compulsory. Yeah.
Okay. I think there's a Patrick Kinyua with a question.
Thank you, Engineer Rangat, for the wonderful presentation. Mine is actually cross-related. When you spoke about steam meters, I would be interested to, if you have a template, just some guide on how to do a cost-benefit analysis that shows the value proposition of steam meter, maybe for guys who have just a condensate meter. Thank you.
As I emphasized, or as I said earlier in my presentation, you cannot use the condensate meter as a steam meter. Like the readings from a condensate meter is not an indication of steam consumption in your organization. No, it's not. And as I said, you see, the operating pressures for the two are totally different. Yeah. The operating pressures are totally different. So, and the specific volume for steam and for condensate are totally different. So you're not going to get the same. You're not. So the best thing is to install a steam meter. You see, there are several steam meters around the market. So I cannot say, I cannot specifically give you a figure. The last quote I got was around 600,000 from Spidax. That was 2 years ago, or 3, something like that. But there are some which are cheaper. Yeah. I mean, proper research on the market. But you see, these on the premise that you are going to do steam management. So maybe the initial capital cost, and you see recouping that amount, because it's not something that will help you save energy, but it will give you information that will make decisions on how to save energy. You get so the cost benefit will not be like you'll get a return on investment on it, but you see from that you'll now use it to do proper energy audit and take measures. So it's something like that is more of a necessity than just an additional thing to the steam system. That's my input.
Yeah, I guess those costs for purchasing meters falls under the group called sunken cost, where you just have to incur falls even categories of research and development. You actually have to forego those costings here. So we have another question from Osia Mwanje.
Before that, I want to emphasize on what Ragata said. Metering does not save energy, but it gives you information to know how to act. It's like going to hospital, you are taken to the lab. In the lab, you are not going to be treated, but the results of the lab will give the doctor an indication of what to say. So it's always good to ensure that everything you meter, everything used there is metered. You normally say you cannot save from what you don't measure. So it's good to ensure that all the measuring equipment are well in order.
Thank you, Eustace. Next time, I'd appreciate if you raise your hand before you chip in. So maybe Osia, next.
Thank you. Thank you, engineer, for making the presentation very easy to understand, even for the non-technical people. So mine is just a non-technical question that I had just for my personal information. Engineer, you had mentioned something to do with the boiler blowdown. Water that has gone round, maybe the system, and as it goes through those pipes and the things there, it gets some impurities, and in the long run, you have to to dispose that water. So on the environmental aspect, this boiler blowdown water, does it have any environmental impact per se negative when it's discharged to the environment? And if it does, then what measures are able to be taken to to reduce their effects on the environment, and if not, if it can still be used, then how or what ways are we able to utilize that boiler blow down water? So that's my question. Thank you.
Yeah, thank you so much. Thank you so much. On the issue of boiler blowdown, why boiler blowdown? The reason why you do boiler blowdown is to reduce the amount of total dissolved solids in the boiler water. And what causes total dissolved solids? As I mentioned, is that most establishments do not treat the feed water to the boiler. And what I mean do not treat is they are not filtered, they are not conditioned properly before being utilized. You'll find that most of the establishments will just get that water either from the bowl straight into the condensate tank to the feed water pump. Or you'll find that they'll get it straight from the river if they are sourcing water from the river, or municipal water for that matter. Then they just feed it directly into the boiler. So over time, that builds up sludge. So that's why you do blow down. However, there are guidelines by NEMA on how to dispose blow down water. There's a soak away pit that you normally blow down the water to, just like the same way you will soak away your sewer water. So normally there's a blow down pit. But what I was saying is you can still utilize that water to recover that heat that goes into the that comes out of the blowdown by recovering it using a flash vessel. Yeah. Once you recover, there's flash steam that will come out, and steam will come out as steam, it will not come out as water with impurities. So that steam can be utilized elsewhere. If the plant is near something, then you can use it to fire in a plant. If not, then if you have an aerator, you can use it as an aerator. If you have, you can still direct it to the Ogden pump to use it as activating the Ogden pump. So there are several ways of it. But as I said, most establishments in Kenya just blow down into the soakaway pit. There are guidelines on how to do it. And normally the NEMA guys come and inspect it. Yeah, thank you.
Okay, thank you. Engineer Lawrence, you can raise your question or comment or addition. I know you are one of the experienced auditor in the sector. Lawrence, I see your hand. Or maybe
You call him Engineer Mangerere, that's how he gets it easily, probably.
no, this is Lawrence Orico. This is Lawrence.
Okay. Oh, Orico.
Yes.
I asked him to come here actually today. It's so good he's around. Maybe we can go to Bill as Orico. Someone tries to look for Orico.
Bill,
yes.
Bill. Bill, you can unmute and make your comment, question, or addition.
Hello.
Yes, Bill, we can hear you.
Are you able to hear me?
Lawrence.
Yeah,
Yes,
we can hear you.
hear you. Continue.
Yes, Orico. Yes.
Yes.
Yes, we can hear you, Rico. You can proceed.
Can you hear me now?
Yeah, we can hear you.
Okay, we have been to some, we have gone to some companies where they use wood in boilers, and they load those pieces of wood in a cage. And then that cage, the one that is fed, the content of the cage is the one which is fed into the boiler. At the end of the day, they say, oh, today we fed 20 kgs or so and so. And then they convert those kgs into kilograms. The question is, why can't the wood be actually loaded and weighed and put into the boiler as a weight, as a mass, not as a volume?
One is that that cage is called a cuboid. It's 1 meter cube. So, and the reason why they do it is because when they are procuring the firewood, they procure it in meter cube. So they have to issue it in meter cube. But the reason why they measure is because one is that, you see, empirically, they've done an experiment and said our cube weighs this much. Perhaps it's on average is normally around 550 to 70 kilograms of firewood. Yeah. So for easy operation, then they just use the cuboid to measure and count now and say we've used this. And that's what I was saying. At the end, you have to sit down and say how many kilograms of, if now you are coming to calculate this efficiency on this screen here, you will have to come and calculate how many kilograms of firewood did you use for you to calculate the gross calorific value. Because you see, calorific value you are given in kilocalories per kilogram. You're not given per meter cube. That's why they have to interpret it. Of course, the main primary reason why they are using cube is because it's always stocked in cubes at the firewood shed. So they have to issue it as cubes. But for weighing, the weighing is for, like when they're converting it to kg, is for now calculating the efficiency. Yeah.
Do you agree with me that kgs do not necessarily weigh the same?
As I told you, it's an experiment. And you see again.
I think we have to, Lagat, let me assist you there.
All right, thank you.
It does not equal, but you see, when any time you put this wood in the cage, it will introduce what we call operational expenses, more operational expenses. But whatever has been done is a good approximation, and to some extent, it doesn't go more than 2%. So it's about ease of operation, because if you have to put a weighing gauge there anytime you want to load, it will be very expensive for the facility. And also probably these are logs of wood, and the people who are loading, they can get tired and sometimes destroy the weighing machine. Then you'll be forced to be buying each one at a time. So the good thing is, and that is why research comes about, where you measure something and you extrapolate what you expect. I think the reason is just an operational issue. But once in a while, you can be going to calibrate.
Assuming that the water content is the same in all cages.
But
the assumption is supposed to. The assumption is supposed to. You have to feed the fuel you feed in that boiler, if it's wood, you should establish is moisture content at any given time. And it has to be like constant, for example, 14.
Okay, Eustace, maybe I can weigh in before Chirchir reprimands me for talking without raising my hand. Who are feeding the boiler are interested in accounting for the money that the wood came in. So the boiler man will say, I fed 3 cubic meters because they paid for the 3 cubic meters. The concept of water content and mass is not accounted for commercially in the operations. But then as an energy auditor, then you now can go to those nitty-gritties. If you want to say boiler number, this factory is using this wood, this is the density, this is the water content. You can even go, you can even do the bomb calorimeter test to see the calorific value. Then you now go to the specifics as an auditor. But then you cannot force the industry to, the operators to be making things that you're supposed to use to do your own computations. So for them, and I think Lagat taught me this 6 years ago when I was talking about stacked versus matchbox arrangement of the firewood. So he was telling him about the issue of people trying to maximize on the cubic meters. So you see, the thinking is different from the way the auditor thinks and the way the facility thinks. But at the end of the day, we need to give this facility are recommendations that are going to translate to monetary savings. So we need to understand the moisture content of the wood. If you want to understand the density, when I'm talking to my students, I always talk about the density of the wood for them to get the proper context of it. You can also go look for the density, ask for the type of the wood, look at for the moisture content, then you can at least you come up with the mass from the volumes that they give you. Thank you.
Asante sana daktari.
Thank you. I don't know if Engineer Lawrence or Rico have managed to establish some connection. If you are able to, then you can.
Yes, are you able now to hear me?
Yes, engineer, you are clear.
Oh, good. First of all, let's thank the trainer for the opportunity. I think he has done it well. And also maybe EPRA for this opportunity. So I only have one question, but two comments just strengthen the process. One thing that I need clarification on is, are we talking about condensate meter when we say we cannot use the condensate meter to gauge the quantity of steam? So I need clarification whether it's a condensate meter or we are talking about feed water meter for the boiler. Because then the question would come that when we convert the amount of water to give a temperature that we have, if the water is really at 80 degrees, if we convert it to steam, are we able to lose in terms of kgs to some extent? That we just need to ponder. But I think maybe a direct link that we will always check, just for those who do not have steam meters, I think the water that we are, the pressurized water that we are injecting into the boiler will give you a better data relating on in terms of if you don't have maybe a steam meter. As opposed to condensate, because condensate is just a small part of it. We cannot always recover 100% of whatever steam that we send to the process. So generally, I think attention of it. So if, because whatever we are injecting into the boiler is a part of condensate and not a part of makeup water. So we need to have, if we have to correlate, then I think there is that aspect of boiler feed water meter, if we are able to do that. So I have seen a few facilities that have that, and I think they are always getting somehow almost an accurate data because we tried to do some correlation, but we find them almost fitting. Number two, if you look at what we are discussing here, I think we also need to encourage some good practice or standards in the industry. Me, I always have problem with this starting of firewood, and then we say it's a cubic, and then we say, because there is so many parameters that determine the calorific or parameters that you can use to establish calorific value of firewood. So you cannot, there is nowhere, I've seen from the literature that I've read, there is nowhere we have a relationship between cubic and calorific value of firewood. So we just need to encourage them, especially it is only found in mostly KTDA. I think other people that are outside KTDA, they have also moved. I know we can say that yes, we procure in cubic, but again, when it comes to now recording what we use in the boiler, I think kg or tonnage should be given priority. The last bit of it is that we need to know, I don't know, because I was on off, there is that aspect of chemical treatment of the boiler water. So there is always a correlation. We need to know if that is not done correctly, then we will always have a lot of problems with that term or that relates to maintenance. And sometimes, you know, that is a major factor that affects the thermal efficiency of some of these boilers. So I think we also need to take note that the water needs to be treated well, and that is a major factor. In terms of blowdown and let's say recovery of heat, that we choose the drain, then there is no aspect of we have specific. We can do the flush in recovery on its own, but then we also need to assess. That's why I always say every good auditor must always be running with it. They don't thermal imager, they can always have a thermal gun just to check whether the steam traps are working well or not. But if they're not working well, again, it doesn't take too much time to just go outside and check whether we are throwing out some flash steam. So if the more flash steam you throw out, you know, it's an indication that some of your steam traps are not working well. So let's just encourage good practices, even if sometimes these facilities do not have that means. But I know in terms of the cubic and kgs, there is always some weighing to it, because when we bring in new firewood sometimes, and there is that small weighing bridge that we pass with the tractor, so they can always record those data and then have them. So let them use the facility of the system that they have. Let us not have much excuse for them. So let's just try to make sure that we have a better guidance. And interrupt auditor, let the auditors do their good work.
Thank you. Thank you.
Otherwise, it's a good presentation.
Thank you, engineer. Thank you for that insightful comments. And a question, I don't know who will pick it up first. Engineer Langat. Engineer Langat, are you still in?
Sorry, I'm speaking while I'm muted.
Okay.
So I think I thank you so much, Engineer Lawrence, for your feedback. And the reason why I was coming out strongly with the condensate, as you said, there's a feed water. There's a feed water meter. Then there's the condensate meter, which is just outside the condensate header. Then now we have the steam meter. As I mentioned and reiterate that you cannot use measurement of the feed water and condensate water to condensate meter to get the approximate by adding up the two or collating the two and assuming the average. As I said, the specific volume for steam at different pressures vary. As I said, even some organizations meter up to the consumption point, that is at the plant, like each dryer has its own steam meter. And the reason why we do that is so that you know how much steam would give you specific amount of product. Because by the time you come condensate, you are talking about leakages, you are talking about change in pressure, change in specific volumes. You will not get an accurate readout. And we are talking about, you can imagine, you are talking about even by the time you're talking about feed water, that's like ordinary water. You cannot compare with the high pressure steam at 10 bar. Those two are totally different. Yeah. And you see, we are talking about kilograms of steam per hour, not volumes. Yeah. So you see the steam condensate, the steam meter now, you should be in a position to say this pressure, this is the specific volume. Yeah. I think all that recommendations that you said, I agree with you. I don't have any other question. It's about being versatile when you're doing in-house audit. I think, Lawrence, I see you raising your hand.
Mute, please.
Engineer.
Yes, Lawrence, go ahead, please.
There was a question that I asked. Yeah?
Yes, yes.
Do we lose mass?
Do we lose? Come up again.
Are we losing mass? If I look at my feed water meters, which will give me 8 kgs per hour of whatever I'm feeding, or liters per hour of whatever I'm feeding into the boiler, and the kgs of steam per hour that I'm getting out. So converting a kg of water to steam, do we lose mass?
But you see, Lawrence, we are talking about Engineer Lawrence. We are talking about the rate of steam generation, not the volumes that you, not the quantities. You get what we are talking about the rate. You will still get the same amount, but at what rate per hour? Are you also going to measure time the boiler was running? So that's why it's important.
I think to chip in, before Chil kills me, it's good to understand this is a thermodynamic process where you exactly always need two properties. And that is one. The other one is immediately this water comes from the feed water. You are not sure that all that water is changed into steam within that given cycle. And that's why Lagat is saying you measure the steam you get immediately. The other point is the condensate return is it's in a different pressure and it's a different temperature. So you might end up messing up your calculations because the boiler itself always holds some water. If you look at the boiler when it's generating steam, it's only less than at the top part of it is only less than 10% of that water which is in the boiler, which is steam at any given time.
Okay, I think, Justus, thank you very much for your input. And for the sake of time, we are now almost 3 hours at, I think, 4 minutes short of the 3 hours time. So thank you, Engineer Langat, for your time, for your presentation. And also thank you to the auditors who have really been patient for the entire stay, the entire period of time. So before I finish or close the meeting, then let me allow Dr. Engineer Felix Musonia to give his closing remarks and maybe close the meeting.
Thank you, Engineer Chirchir. I've just written somewhere in our pair group that from next week, I'm waiting for audits in this place, which will not have discussed boilers. We reject them and send them back to the sender. Anyway, I'm saying it's a job, it's not a joke, it's quite serious, unless we saw you in this meeting. But I think we've seen from the contributions from the engineers there, Engineer Mangerere, Engineer Orico, Eustace, and Engineer Langat, it's quite an exciting process, especially those of you who interact with the boilers. It's quite exciting. And as we always say, you cannot know everything. Like if you want to know about chillers in this office, we go to Eustace. If you want to know finance, we go to Chirchir. If you want to go to know solar, we go to Hasib. The same way in the industry. And because Engineer Lagat is part of our group, is in a pair group, it does no harm for me to go to the facility and look at this boiler and realize this boiler, I cannot do anything about it. And then contact the engineer and tell them, please, can you assist me in this section of the audit? And this brings us the issue of undercutting, because I know some people do undercutting here. So if you really bargained very well for an audit and you can provide, you can see the difference. Someone is talking about 700 kilograms of med tea, another one is talking about 300 or 200 kilograms of med tea, same fuel. So if we really price our audits nicely, but then we involve the correct auditors, the correct experts, then they come in, they assist us, and you really prove to the facility they are going to save. We are going to bring back, if I'm saying bring back, I know Bill and Chris and Orico, all the auditors know that. We'll bring back up, for that matter, the cost of doing audit, because see, we need to get money from it, and all of us are auditors. So if we do such a good work like the one Engineer Lagat is showing us, then you can prove, and they do save. Imagine saving maybe more than 3/4 of what you've been using in fuel. That can be a very good thing. And that's why we want to keep on bringing experts from the industry to talk to us, so that you don't think we are only sitting in our chairs here and trying to dictate. So it's good we've seen from engineers. There are many things I've written very many notes here, even that mechanical engineer like himself, but there are things I don't know that he's been teaching here. So let's endeavor to improve. He will send us the notes. Actually, we already sent the notes. We will also upload this on YouTube, on our channel, and then you can access this anytime. Before you want to go and audit, you can maybe keep on reading it. And then you can also get Engineer Lagat's number from the IPAIR group, I think is there. So to Engineer Lagat, thank you very much, Engineer. I've been talking to you for the past 5 years to come and do this session. But
thank you so much. Thank you so much.
Yes. And I now people see the value, what I was insisting that at least one day you have to come and teach us. And you have shown us a good example to, I know we have also very many young engineers here, on the importance of specializing in a thing and becoming very good in it, because you've been teaching so flawlessly for the last 3 hours without getting tired, without showing any sign of capitulating. That's a very good thing because you are an expert in the area. So thank you, and we hope to continue next week. Before I close, we will have a similar session. Engineer Sequoia said he was somewhere in the industry. I think he was training guys on pumps on site. So probably next week, Engineer Sequoia will have a session with us. Then we'll have Engineer Chirchir with this session. Engineer Chirchir, we work with him here to talk about finance. Then Engineer Sequoia will talk about pumping systems. Then I think we'll have done with this round. But then next month, we'll have just a round table with the auditors. I'll want to hear a lot from Orico because I see him working in so many facilities. At that time, we'll just want to have a discussion, general discussion on how to improve audits. We might have it probably in Strathmore University. And this is a sponsored event by Sustainable Energy for All. So the sponsors, I ask them to do that to make sure that we auditors can also meet. Then we exchange notes on how to improve the quality of our work. Otherwise, I'll say thank you very much. If there are guys here who have CEMs and you don't want to come for licenses, please apply, do audits, talk to Orico, talk to Chris is here, talk to Becky, talk to Engineer Magerere. There are so many people who are in this meeting who are auditors. You do audits, 3 or actually do 5. Yes, 5 of them and really understand them. Then you come for the license because the number of our auditors is shrinking. I think most people want to do other things. So we want to have more auditors doing the work. Others, thank you very much. And at this moment, it's 5:30. I'd wish to close the meeting and ask you to leave at your own pleasure, or you can remain logged in. Thank you, guys. Bye.
Thank you. Thank you. Bye.
Thank you,
Thank you, everyone.
And have a good evening, all.
Mtu anitie sapa bwana.
Kavoi, you are raising the question, your hand after the meeting.
Richard,